Hi, and welcome to the presentation ADI, a simulation platform for automated driving system. My name is Maxime Sainte Catherine, and I am a research engineer here at KTH in the mechatronics division. My role is to maintain and develop the ADI platform. Today, in this presentation, we are going to see an overview of the ADI platform, its current status, and its future plans. But let's start by introducing KTH. KTH is Sweden's largest technical university and consistently ranks within the top 50 worldwide in engineering and tech. It has more than 10,000 students and around 4,000 full-time employees. Here, at the mechatronics division, we have more than 40 full-time employees, out of which more than half are working in automotive or related fields. Our funding comes mostly from external sources, and we are working close to the industry. We are part of European projects and a Swedish national research project. To give an idea, each year we have approximately 60 master's students in the mechatronics program and approximately 60 other students in the embedded system program. Those students usually end up working with companies like Scania, Ericsson, AVL, and Volvo. Considering that more than half of the division is working on automated or related fields, and considering that we have many smaller projects, such as master thesis or student projects that are also focusing on automotive, and knowing that automated driving systems are inherently complex, as they require solving a multitude of tasks from many different domains, ADI was created to provide a simulation platform for automated driving systems. The goal of ADI is to provide command-based functionalities that can be modified as needed. An example would be a researcher that focuses on motion planning. This researcher can use the ADI platform, replace the part of code that performs the motion planning by their own approach, and see the impact on the whole system without having to re-implement the whole surrounding simulation. So it saves a lot of time, and this explains the goal of ADI to provide this base functionality and to be modular, which we can see in the platform architecture. So here we see ADI's architecture. ADI is divided into two parts. On the left side, we have the environment, and on the right side, we have the autonomous driving intelligence. The environment can be thought of as a plant, and the autonomous driving intelligence can be thought of as a controller. This separation layer between the environment and the autonomous driving intelligence makes the transition between real world and simulation easier. If we have a closer look at the environment, it can either be the real world or it can be simulation. In the case of simulation, we have integrated the simulation software PreScan, which we have interfaced through Simlink with ROS. ROS is our middleware, and thanks to its design, with the concept of nodes and packages, ROS provides a lot of flexibility and a lot of modularity. On the autonomous driving intelligence side, we have two separate and independent control channels. The nominal channel, which perform tasks such as perception, decision-making, and planning. Those packages can be replaced individually. And we have the safety channel, which was entirely developed here at KTH. The role of this safety channel is to monitor the nominal channel and to make sure it stays within its safe operational envelope. Once a control signal is being generated, it is sent back to the environment and we have our control loop. In this control loop, we can perform some fault injection. And examples of fault injection could be to manipulate sensor data or to kill rust nodes, which we can do with the ADI platform. With ADI, we can create simulation worlds. The first way to create a world is to do it manually, as seen in the video, by dragging and dropping elements. This is an easy and intuitive way to create simulation worlds and scenarios and allows to prototype quite fast. The alternative, more automated, is to import simulation world. As we can see here with a KTH campus that was imported from OpenStreetMap. So the left picture is the map in OpenStreetMap and the right picture is a simulation world as we can see it in our simulation software. This more automated way of creating simulation worlds is more scalable as we can generate hundreds of simulation worlds by doing so programmatically. Once those worlds are imported, they can also be manually modified and improved to get closer to reality, as we can see here with improved buildings and textures for KTH campus. Once the simulation world is created, using ADI, we can programmatically generate two kinds of map. The first one, road network map, is a map used for navigation. So using ADI, we can create this map in a known format, and it contains all the data useful for navigation, such as lanes position, direction, traffic signs, and traffic lights, and other. So this is one layer of map, and the other one is point cloud map. The point cloud map is a set of points in three-dimensional space that is used for localization. This one can also be generated using the ADI platform from the simulation worlds or from the real world, as we can see in this video, where the map of KTH campus is being recreated. Those two maps, those two layers of maps, are the only a priori knowledge that is given to the autonomous driving intelligence. The ADI platform has a support for several sensors, such as cameras, radar, and LiDARs. We have worked on image classification, and ADI allows to generate big data sets using simulations, and we have used those to train a neural network to assign tags to detected objects. We saw in the architecture that ADI, and more specifically the autonomous driving intelligence, was composed of two independent control channels. In the following video, we are going to see how those two channels interact together and how to go from the creation of a world to running a simulation. So here we can see KTH campus on OpenStreetMap and its digital version, digital twin, with the Ego vehicle here in the simulation software. Now we have switched to the autonomous driving intelligence point of view, where we can see the two layers of map that I mentioned previously. The white points are representing the point cloud map, while the white lines are representing the road network map used for navigation. And those two are the only a priori knowledge given to the autonomous driving intelligence. What we see now, on the other hand, those color dots represent the LiDAR data, which is real-time data. And based on this data, we can perform some detection, some clustering, some localization. We have 3 layers of planning: global planning, local planning, and motion planning. So all this is part of the nominal channel. And we will see now an occupancy grid, which is the representation of the surrounding environment by the nominal channel, which is simple by design. So now our Ego vehicle is driving on KTH campus. The blue path that we can see on the left side of the video is the global path, while the yellow and red trajectories are the local trajectories. Here we can see an example of an added infrastructure. Indeed, there are no traffic lights on the actual KTH campus. But using the ADI platform in simulation, we can add new infrastructures and see the impact not only on the environment, but also on the system. Here, in our case, the Ego vehicle stopped as the traffic light was red. Now we are going to generate a fault in the LiDAR sensor, and as this fault is detected, the safety channel performs a safe stop maneuver. And as we will recover from this fault, the nominal channel will continue driving. So I want to emphasize the difference in purpose between the nominal channel and the safety channel. The nominal channel aims at reaching a goal, while the safety channel monitors the nominal channel and makes sure that it stays within a safe operational envelope. So now we have seen how to run one simulation, but using the ADI platform, we can run thousands of simulations thanks to test automation. So with test automation, we can run multiple simulations with different parameters. We currently support over 100 parameters, and in this video, we are going to see a small subset of test automation of the parameters that can be changed. So we can change the simulation world, and we can change, illustrated here, the weather condition from sunny weather to foggy to rainy. Furthermore, we have implemented a support for open scenario. This provides more maneuverability as we can control the behaviors of actors and how they interact together. But it also provides an easy way to specify the scenarios we would like to run. I'm going to describe one scenario here. So there's currently a research being done about the disturbance on LiDAR sensors, and ADI is contributing with the experimental part. So one of the scenarios we are running for this experimental part is illustrated here. The Ego vehicle drives in its lane, and further on the road, on this side of the road, there's a pedestrian that once close enough to the car will start walking until the middle of the lane. The purpose of this experiment is to measure the disturbance of RAIN on the functionality, that is object detection, performed on the LiDAR data. So here we are going to see two different runs. Some of the parameters we can change between those thousands of experiments that we are running are the speed of the ego vehicle, the distance at which a pedestrian will start walking toward the middle of the lane, and the RAIN model parameters. So here we saw the ego vehicle had a low enough speed and the pedestrian started walking far enough, and the ego vehicle managed to avoid an accident. With this second experiment, we can see that with a faster speed and with the pedestrian starting to walk earlier, the ego vehicle has an accident with a pedestrian. So that was one example. Now that we know what can be done with the ADI platform, let's have a look at its future plans. Here we can see a timeline of the project ADI is part of. Some I would like to mention are Insect, in which we will focus on security, Campus 2030, in which we will focus on infrastructures, and TECOSA, a research center, in which we will focus on edge computing. Those three will lead to a shift from ADI focusing purely on automated driving to ADI aiming at becoming an intelligent transport system testbed here at KTH. To do so, we are currently working on real-world usage. ADI has been ported to the NVIDIA Drive PX2, and the goal is to have it running on a real vehicle. We have an open application at Transportstyrelsen, the Swedish transport agency, to be allowed to drive autonomously on the road here on the campus. As we'll be able to perform more real-world experiments, we'll also gather more data from the real world. And we want to use this increase of data to improve the fidelity of our models, to improve the simulation worlds, but also to improve the motion prediction for other actors, such as cars or pedestrians. We are working on increasing the scalability of test automation. Right now, we can run thousands of experiments, but we would like to run 10,000 experiments. And we would like to be able to move from the single computer that we have here physically to clusters, such as the clusters that we have here at KTH. This would free resources. Those computers that we have physically, we would like to keep them for development. And it would also allow to run more tests and perform a more in-depth safety analysis. We are working on modeling the system, as you can see here, with a model of the ADI platform done in the open source tool Capella. This modeling allows us to do safety analysis. ADI aims at becoming open source. Open source not only with the code, but also with the safety case and the methodology. All those elements combined, and adding the fact that we have 5G here on KTH campus and the fact that we'll focus more on edge computing, ADI aims at becoming an open testbed for intelligent transport systems. I want to thank you for your attention. If you would like to know more about ADI, you can visit our website. And if you want to get in touch with us, you can do so at the following mail address, adi@md.kth.se.